Hello everyone. In the next 10 minutes, I'd like to summarize my research this summer for the Medallics Lab in the ECE department at the University of Toronto. The title of my project is Extending the Capabilities of Me-Series Algorithms for Radar Cross-Section Calculations. Let's provide some context first. All objects interact with electromagnetic waves, typically through absorption, transmission, and scattering. Given an incident wavefront that impinges on an object, a fraction of the electromagnetic power is scattered in an arbitrary direction. The radar cross-section is a measure of how much power is scattered by a unit of incident radiation. RCS can be thought of as the electromagnetic signature of an object. One way of calculating the RCS involves using the Me series, which breaks down the scattered electric field into a sum of spherical harmonics, somewhat similar to a Fourier transform. Me-series solutions yield results for scattering by objects with polar symmetry, such as spheres and cylinders. In practice, the radar cross-section depends on several factors, such as the frequency of the incident electromagnetic wave, the geometry and the material of the object, as well as the observer's position. Scattering behavior changes significantly as a function of wavelength, and it's important to calculate the RCS accurately for a wide range of frequencies. So now that we know what radar cross-section is, but why is it useful? Actually, RCS is a key metric in almost all radar imaging applications, and these include autonomous navigation, target recognition, and military reconnaissance. These high-stakes applications require precision and robustness, which in turn demands accurate calibration against test objects. And so you can see in this picture that metallic spheres are commonly used to calibrate equipment before measuring the actual radar cross-section of, for example, a fighter jet. Such measurements are needed to identify and discriminate threats using radar in combat situations. And such calibration procedures take place in countless of aerospace and defense companies, as well as research institutions across the world. Another area where radar cross-section is useful is in computational electromagnetics, which, among other things, is critical in the design of consumer technologies such as cell phone antennas, wireless communication circuits, and high-frequency central processing units. It is vital to ensure that the numeric computational electromagnetic solvers are accurate so that these technologies work as expected. Typically, accuracy is established if numerically obtained results are consistent with analytical solutions to well-known problems, such as scattering by a dielectric sphere. Since the Me series is calculated analytically, researchers frequently verify the numeric RCS with the analytic Me results before moving on to more serious simulations, like you see here. However, computational electromagnetic solvers require a lot of time and resources. And this is an area of a lot of research. So the Medallics Lab is also researching and developing novel electromagnetic solvers and was looking for ways to validate their algorithms. One project in collaboration with Advanced Micro Devices is involved with modeling the crosstalk and electromagnetic noise inside central processing units. This is a very challenging problem because semiconductors behave as lossy dielectrics at gigahertz frequencies, and even partially conducting elements begin to radiate electromagnetic noise. So at the beginning of the research project, I did an extensive search for an open source Me-series solvers. However, these existing code libraries were not able to return the results for the combination of high frequencies and high conductivities, both of which were required for the work at Medallics. As you can see in this picture here, we were expecting 4 different curves to show up for 4 test cases, each one with a different conductivity. But the code returned not a number for the 2 high conductivity cases. So we suspected that there was a numerical issue preventing the code from producing results, So my job was to find and fix that issue. Out of the many code libraries I examined, we selected the MATLAB sphere scattering for further debugging due to the code's readability and documentation. Each line in the code was referenced against formulas in the textbook for accuracy. Now, part of that mean-series calculation involved evaluating Bessel functions. It became apparent that for the high conductivity and high frequency regime, the Bessel function evaluated to results that approached 0 and infinity. This would cause MATLAB to return not a number when these values were divided by, due to a division by 0 error. To fix this, the Bessel functions were multiplied by an exponential scaling factor derived from their asymptotic form. The scaling factor later cancelled out from the calculations entirely. Thus, the physical quantities were preserved while avoiding the numerical issues. Working on this issue, it became apparent that the code was evaluating too many terms in the Mie series. For a given frequency, terms would converge, become very small, until their result is not a number, due to the first numerical issue. Now, hence, since the sum of these terms would also be not a number. So to fix this issue, a pilot calculation was implemented to determine the greatest number of terms necessary to calculate the sum to floating point precision. The remaining terms in the series were adaptively truncated from the calculation, since they are too small to make a difference. In the combination, these two modifications enabled calculating the RCS for higher frequencies and conductivities, thereby reducing the computation time while maintaining accuracy. In the plot on the right, which is obtained after these fixes were made, all four curves are shown as expected, so that the code now works for the high conductivities. Now, to ensure that the modified code remained accurate after my changes, the results from the analytic Mie code was compared to a numerical solver in a variety of test cases. The numeric solver was independently validated to commercial tools, so that the results are trustworthy. And the plot here shows very good agreement between the code I was modifying in blue dots and the numeric validation results in red dashes. And to automate the validation process, I also wrote several user-friendly interface functions that calculate radar cross-section profiles over a range of positions around the sphere, frequencies of the incident waves, and the sphere material. The interface functions afforded convenience and time savings, helping streamline the validation workflow at Medellix. So to summarize, my work this summer has enabled the efforts to validate novel computational electromagnetic solvers at the Medellix lab. And furthermore, this improved library was translated from MATLAB to Python to make the code accessible to a wider group of researchers and individuals. While this project is wrapping up, there is still opportunity for further work. And this code would greatly benefit from additional functions for computing the RCS of concentric spheres, cylinders, and planar media. With these extensions, the code can be applied to a larger variety of electromagnetic scattering problems that arise in the design of advanced technologies such as metasurfaces and CPUs. And since the analytical expressions have already been derived by other researchers, further work will only involve implementing these formulas in code, validating them against numerically obtained results, and debugging when necessary. To finish off, I'd like to highlight some potential impacts of this research, both in Canada and globally. So by providing accurate analytical solutions, this code can help validate numerical results obtained during the design process of antennas and CPUs, help perform more accurate calibration of radar imaging systems, establish the accuracy of novel computational electromagnetic codes, and finally, since we'll make this open source, countless of other individuals can also make use of this library and benefit. Finally, I'd like to acknowledge the sponsors whose financial support made this research project possible. Thank you for your attention.